Welcome back, everyone, to another Explainer. Today, we are unpacking a massive and, frankly, awe-inspiring engineering mystery. Have you ever looked up at those towering skyscrapers? The ones that literally scrape the clouds, and wondered, how on earth are these things surviving? Like, when the ground literally shakes beneath them with terrifying force, why don't they just come crashing down? Well, today, we're diving straight into that. We're going to uncover the secret, hidden physics of earthquake-resistant skyscrapers. And trust me, by the end of this, you are going to see the city skyline in a totally different way.
Okay, picture this. You have a tiny 2.5-foot scale model of a building. With just the absolute slightest tremor or mini-quake, that little model shakes violently, right? It looks super unstable, like it's ready to tip right over. But then, compare that to the majestic Taipei 101. We're talking hundreds of feet up into the sky. When a massive earthquake hits, this colossal, incredibly heavy structure stands almost perfectly, impossibly stable. It totally defies common sense. I mean, why does the giant structure survive when the tiny model just thrashes around so easily? Well, to figure out this skyscraper-sized secret, we actually need to look at something much, much smaller, and honestly, something far more familiar to all of us.
Section 1. The Science of the Swing. Now, every swing has its own natural frequency of oscillation. Think about when you sit on a playground swing. If you just let it move back and forth completely on its own, no kicking your legs, no pushing, it swings at a very specific built-in rhythm. That specific physical setup has a natural pace that it just wants to sway at. In the world of physics, we call that swaying motion an oscillation, and the specific speed of that natural rhythm, that's its natural frequency. Make sure you keep that concept in the back of your mind, because it's the invisible underlying force behind literally everything we're exploring today. So, let's say we want to increase the swing's amplitude. If we want it to swing higher and higher, covering way more distance with much more energy, what do we actually do? Well, think about when you're pushing a friend or a little kid on a swing. You don't just push them randomly at any given second, right? No. You wait for the exact perfect moment. You apply your push in perfect time with their backward and forward motion. You naturally match their rhythm to make them go higher.
And this brings us to a huge concept, resonance. In the precise language of physics, when you match the frequency of your applied force, so your push, to the natural frequency of the object, the swing, you create resonance. This perfect matching of frequencies dramatically increases the energy and the amplitude of the object. The swing goes way higher, the energy builds and compounds, and the whole movement just gets bigger, faster, and way more intense. But hold on, think about this in the context of our skyscraper. In a massive building during an earthquake, that compounding energy and swaying is exactly what you desperately want to avoid, right? A building swaying bigger and bigger because of resonance, that means catastrophic collapse.
Moving on to Section 2, Damped Oscillation.
So, damped oscillation. This happens when the frequency of the applied force does not match the object's natural frequency. Imagine pushing that playground swing again, but this time, you push completely out of rhythm. You push when the swing is coming right at you, or just at totally random, mismatched intervals. What happens? The swinging slows right down. The kinetic energy is absorbed, it's disrupted, and basically canceled out. The movement damps, or, stops. By intentionally applying a mismatched frequency, you totally kill the energy. You literally stop the swinging motion dead in its tracks.
Which leads us to Section 3, Use of Dampers in Buildings.
Okay, to stop those really dangerous oscillations we just talked about, engineers use a super heavy object called a damper, and it's carefully suspended right in the dead center of these massive buildings. Think of this damper as a colossal pendulum, or like a massive internal counterweight just hanging deep inside the skeleton of the skyscraper. When the earth starts to shake and the building naturally wants to start swaying, this massive, heavy object is right there to act as that out-of-rhythm push. It's specifically designed and placed to counteract the building's movement and absorb all that terrifying kinetic energy from the earthquake. But listen, here is the golden, absolutely unbreakable rule of physics for this whole thing to work. The damper's natural frequency must never match the earthquake's frequency. Remember our definition of resonance from earlier? If the damper's frequency accidentally matched the earthquake's vibrations, well, it would be exactly like pushing the swing perfectly in time. It would amplify the shaking, feed the energy, and the entire structure would literally tear itself apart. So to successfully damp the oscillation and actually save the building, the damper deliberately operates at a completely mismatched frequency to the seismic waves rolling through the ground.
Let's put this brilliant system together step by step.
First off, step 1, an earthquake hits, sending these violent kinetic waves right into the foundation of the skyscraper. Step 2, as the building reacts, that massive damper inside springs into action, swinging and introducing a perfectly calculated, highly mismatched frequency right against those incoming earthquake waves. Step 3, because those two frequencies clash so incredibly heavily, the dangerous swaying is actively slowed down. The oscillation is successfully damped. And finally, step 4, because of that clashing, energy-absorbing damper, the hundreds of feet tall building remains completely stable. It safely rides out the tremor, while that 2.5-foot scale model without a damper completely falls apart.
Seriously, how incredible is it that the very same simple physics of a playground swing protects millions of lives inside the world's tallest buildings every single day? The invisible forces of nature can be totally terrifying, for sure, but by understanding them, we can build structures that completely defy the odds. So what does this all mean for us? Well, the next time you see a colossal skyscraper standing tall against the skyline, or honestly, even just walk past an empty swing set in a local park, I hope you remember the invisible science at play. Mismatched frequencies, damping, and just brilliant engineering taking an everyday concept to save lives on a massive scale. Thanks so much for joining me for this explainer. Keep learning, keep wondering about the incredible world around you, and I'll catch you on the next one.